in the last lecture we had been looking at the state space model. We saw that the state space model can be defined in terms of two equations, the observation equation and the state equation. And we saw that this involves a number of parameters. So, in today's class what we will be looking at would be to estimate these parameters. Now, remember that if you look at the state equation, the latent variables themselves are unknown. So, we will need to find a way to estimate the latent variables, so that we are able to estimate the parameters. So, remember the problem in this case is that only the xt's in the first equation are known, everything else is unknown. We will be interested in the parameters, but to do that we require the latent variables to be either estimated or some values of it given. The process by which this is done is referred to as the Kalman filters. We will have a look at the Kalman filters in this class. To estimate the parameters of the state space model, let us very quickly go through the model itself. So, we have xt, which is the observed series, and we have d state variables, which are w1t to wdt, which we write as a vector wt. Alpha is the vector of constants, and using this we write the observation equation as xt is equal to alpha prime wt plus epsilon t, where epsilon t are the model errors, which are white noise with 0 mean, and variance sigma epsilon square. The state equations which are formed from the latent variables are wt is equal to phi wt minus 1 plus k eta t, where the eta t's actually act as the errors, and these are IID with 0 mean and variance sigma. Phi and k are of course the parameter matrices. So, this is the setup that we have got. Now, the question is, how do you estimate the parameters which are alpha and sigma epsilon square from the observation equation, phi, k and sigma from the state equations. So, the first three are the parameters involved in the equations themselves, and the last two are the variance parameters. The problem here is that the state variables wt themselves are unknown. So, in fact, we know nothing about the state equation. Everything in the state equation is unknown to us, and only the xt in the observation equation is known. So, how do you actually get the estimates of the parameters not only of the observation equation, but also of the state equations? So, we will do this by the likelihood method. So, assume that epsilon t follows the normal distribution with mean 0 and variance sigma epsilon square, and eta t follows the normal distribution with mean 0 and dispersion matrix sigma, where we will assume that sigma is a diagonal matrix. So, the elements are uncorrelated to each other. So, having assumed normality, it is now easy to write the likelihood. We will see that the likelihood can be decomposed into the product of the conditional distribution. That is, we have a joint distribution which is f x1, x2, xn, but what we will do is we will start with f x1 into f x2 given x1, f x3 given x1 and x2, etc. So, in general it will be f xt given x1 to xt minus 1, that is given the past, and since we are looking at a time series which is causal, we will be primarily looking at this sort of a distribution. Now, let us take mu t given t minus t as the conditional mean, that is, it is expectation of xt given the past values xt minus 1 to x1. Similarly, mu t would be the conditional variance of xt. Once we are given mu t given t minus 1 and mu t, we can write the prediction error as xt minus mu t given t minus 1, and we will call this Et. So, Et is the prediction error. Now, having defined Et, we can write the log of the joint distribution as minus of 1 by 2 log of twice pi minus 1 by 2 log eta t minus eta t square by twice mu t. This is the usual normal distribution. And if you look at the log likelihood now, it becomes minus n by 2 because you are taking the product. So, it becomes minus n by 2 log of twice pi minus half summed over log eta t minus half summed over Et square by mu t. So, we will need to look at this, but the problem is that we have not observed Et and eta t yet. So, what would be Et and what would be your mu t in this? That is what we will need to look at. That is the problem we have with the state space model. We have a lot of unknown state variables. Now, to solve this, we use what are referred to as the Kalman filter. And the Kalman filter is a recursive procedure which at each step gives us updated values of the unknown latent variables, and we will see how it works. So, assume that at the t minus 1th step, since we are given xt minus 1 up to x1, we have the estimator wt minus 1 of capital Wt minus 1. So, given the past observations up to time t minus 1, suppose we have Wt minus 1, and this Wt minus small Wt minus 1 is the minimum min square error estimator of capital Wt minus 1. We have this. Of course, this would not be given, and we will see how we can actually get this also, but for the time being assume that for the previous step this is already obtained. And once we have obtained this, we will write Ct minus 1 as the corresponding covariance matrix, which again is obtained till the last time point t minus 1. Next, let the conditional expectation and covariance matrix of Wt, that is the latent variable, given the past values of the observed series xt minus 1 to x1, be Wt given t minus 1. So, in this case, unlike the previous one, this is expectation of Wt given the past, and similarly you can define the covariances in this case as Ct given t minus 1. This is again based on Wt, and in that case it is easy to see that we can write this as Wt given t minus 1 is phi of Wt minus 1. Why is this so? What is Wt given t minus 1? It is expectation of Wt given the past. But if xt minus 1 is given, then we can assume that phi t minus 1 is given. Rather, we can assume that phi of Wt minus 1 is given. Now, let us see how we can get Wt into t minus 1. You see, Wt given t minus 1 is given by expectation of Wt given xt minus 1 up to x1, and since given xt minus 1 etc. means Wt minus 1 is given, let us look at the observation equation. In the observation equation, we have xt is equal to alpha xt Wt plus epsilon t. So, that gives us a relation that xt minus 1 known means Wt minus 1 is known. In fact, if you go now to the state equation, we will find that Wt depends on phi Wt minus 1 plus the error, and the error has expectation 0, Therefore, Wt given t minus the past would really be the first term, which is phi Wt minus 1. So, we get the first relationship of the prediction equations. And similarly, Ct given the past would be phi of Ct minus 1 phi prime plus k sigma k prime. How do you get this? Again, Wt is equal to phi Wt minus 1, and we know Wt minus 1, we know Ct minus 1, which would be the variance, and therefore it becomes phi into the dispersion of Wt minus 1 phi prime, and since it is uncorrelated to the error variance also comes out as k sigma k prime. So, we get these two equations and we call this the prediction equations, because given Wt minus 1, we can now predict what Wt is going to be like. Similarly, given Ct minus 1, we can predict what Ct is going to be like. Now, let us look at xt is equal to alpha prime Wt plus epsilon t. Now, if we look at the conditional expectation of xt, we have seen that this is mu t given t minus 1. This would be given by alpha prime phi Wt minus 1, because the epsilon term has 0 mean, so that does not count, and expectation of Wt we have seen is phi Wt minus 1 given the past, and therefore, we can write this as alpha prime Wt given t minus 1. So, that would be the conditional mean given the past, and we will define the prediction error as Et is equal to xt minus this conditional mean. Therefore, it is xt minus alpha prime Wt given t minus 1. Similarly, nu t, which is the conditional variance, would come out as alpha prime Ct given t minus 1 alpha plus the error variance, which is sigma epsilon square, and we will require this to construct the likelihood. Mind you, the likelihood involved the Et and the nu t's. But the problem is, we said that we are given Wt minus 1, Ct minus 1. How do you get this? So, suppose we are given this, then how do you get Wt and Ct for the next step? So, let us look at it this way. As a new variable, xt becomes a variable. So, we have done this up to t minus 1 somehow, a new variable xt comes in now, and we have to get Wt and Ct for this new variable, so that we can proceed to the t plus 1th step. So, once we get this, we set up this regression model. On the left hand side, we have this two variables here, Wt given t minus 1, which is basically itself a vector, and we have the new observation xt. Now, if you write this as I alpha prime Wt plus Wt given t minus 1 minus Wt by and epsilon t, just look at the first set of equations, that is Wt given t minus 1 on the left hand side. What we have on the right hand side is I into Wt would be Wt, and plus Wt given t minus 1 minus Wt, actually the capital Wt cancels off, and we have an identity as the first set of equations. As for the last equation, it is xt is equal to alpha prime Wt plus epsilon t, but that is exactly what we have in the model. So, we can take this together. The first is a set of identities which we put slightly differently, taking Wt given t minus 1 as capital Wt plus Wt t minus 1 minus Wt, and the second as the original observation equation itself. So, the left hand term we can look at the response as our y in general in a regression model. On the right hand side, we have Wt, which acts as our x in the regression model, and I and alpha prime acts as a coefficient beta, whereas the other term, the second term, acts as the error in this regression model. But then if you look at the error, and if you look at its mean, is going to be 0, expectation of Wt given t minus 1 and Wt, that would actually give you 0, and expectation of epsilon t is 0. So, the dispersion basically in this case would come out to be uncorrelated, and it will be a diagonal which would be Ct given t minus 1 and sigma epsilon square. Since the error dispersion is not an identity matrix, that is the model, in this case the regression model is not spherical, we will need to apply the generalized least squares method. Now, as you know, if you apply the generalized least square method, we would get Wt as beta, which is 1 alpha in this case, then the dispersion of the error inverse, which is Ct given t minus 1 and sigma epsilon square as the diagonal, and 1 alpha prime as the second beta. That would be your x's in fact. So, x prime into sigma inverse into x whole thing inverse into x prime sigma inverse, that is the variance inverse, into y. That is what we generally get, and that is how we write it. And then after a little bit of algebra, we can write this Wt as Ct given t minus 1 minus 1 by dt into Ct given t minus 1 alpha prime Ct given t minus 1, with Ct equal to Ct given t minus 1 minus 1 by mu t Ct given t minus 1 alpha prime Ct given t minus 1. Now, the question is, once we have done this, we have come up to the t minus 1th step, and then how should we update the Wt and Ct values? We have been assuming the Wt values and the Ct values up to the t minus 1th step, but somehow we have to get this, and we will see how we actually do that. So, given xt, how do we actually get Wt and Ct so that we can use them when we go to the t plus 1th step? Now, xt becomes available, we actually construct this regression model Wt given t minus 1 and xt. So, the first are the set of this is a vector of the state variables, predicted state variables, and xt is the observed variable. This is equal to 1 alpha prime Wt plus Wt given t minus 1 minus Wt by epsilon t. And you can see that the first set involving Wt given t minus 1 on the left hand side you have the small w. This is basically an identity, because if you look at the right hand side, the first term corresponding term would be Wt, and then you have small Wt given t minus 1 minus Wt. So, that actually negates each other out. Whereas, for the last term, which is xt, which is a scalar in this case, is equal to, if you look at the right hand side, it is alpha prime Wt plus epsilon t. So, this is the observation equation that we have. So, in this vector form, the first set is primarily the d state variables, which is now put in a identity form. The right hand side cancels off the capital W's and you get Wt given t minus 1, and the second or the last element in this case is the observation equation. So, we can put this in the regression form, and when we do that, the left hand side actually gives us the response in a regression model. We will call it the y. The right hand side has Wt, which is your betas, and one, this case I and alpha prime, which would act as the x, this is the design matrix, and the last term on the right hand side, the second one, is the error vector. Now, the error vector in this case is, it's easy to see that the expectation of this is going to be 0, because expectation of Wt given t minus 1 minus Wt is 0, and so is the expectation of epsilon t. And it is a dispersion which is given by a diagonal matrix Ct given t minus 1 and sigma epsilon square, the other elements being the off diagonal elements being 0. Now, since in this case the dispersion is not an identity matrix, we generally use the generalized least square method, because you have this as a heteroscedastic sort of model, because you have Ct given t minus 1, which you will have to take account of, and hence we will be using the generalized least squares. Now, if you apply the generalized least squares to this model, what we land up with is, mind you, your beta is acting as your Wt here. So, you have the estimate of Wt as small wt, which is x, which is 1 alpha x prime, into the variance, a dispersion inverse, which is Ctt minus 1 and sigma epsilon square on the diagonals and 0 elsewhere, into x, which is I alpha prime, and the whole of the inverse of this. And then you have I alpha Ct given t minus 1, 0, 0 sigma epsilon square inverse, and then you have the y vector, which is the response vector, Wt given t minus 1 xt. The inverse looks complicated, but if we apply some of the standard matrix inversion theorems, then you can get this inverse as Ct given t minus 1 minus 1 by nu t, Ct given t minus 1 alpha alpha prime, Ct given t minus 1. And then you have the remaining part of this x prime sigma inverse y, and you multiply that with the inverse form and you get your Wt. Now, remember that this inverse part actually also leads to the variance. So, that will give you your Ct. So, basically the inverse actually gives you Ct, and this Ct into the second component actually gives you your Wt. So, we now can update Ct and Wt. Remember and look at this, everything on the right hand side is given from the previous step, all the variables. Of course, the alphas are unknown, and those are the things that we will be estimating. In this module, we had been looking at the state space models and how to estimate the unknown parameters in the model. The problem was that the state variables themselves are unknown and hence needed to be estimated before we can estimate the parameters. We saw how we can do this through what is referred to as the Kalman filters. We have a set of prediction equations and updating equations which allow us to form the likelihood function, and then we can solve the likelihood to get the unknown parameters. We will move on to the properties of the state space model in the next lecture.